Hello and welcome to Algebra 2 Lesson 80. In this lesson, we're going to learn about nonlinear inequalities. So hopefully at this point, everybody knows how to solve a linear inequality in two variables and also how to solve a system of linear inequalities in two variables. I just want to take a few minutes here and review how to do this type of problem. Pretty much everything we're going to do in this problem is going to carry forward into solving a nonlinear inequality. And then also, the same concepts are going to be used when we solve a system of nonlinear inequalities. If we have a problem like 6x plus 2y is greater than 12, what's the first thing we want to do? We want to find the boundary. And in this case, it's going to be a boundary line. But later on, if we're working with nonlinear inequalities, we won't have a boundary line. The boundary will be a different shape. But the boundary is an important concept to get down. When you're on the coordinate plane, the boundary is going to separate the coordinate plane into two regions. One region is the solution region, so all the points there will satisfy the inequality. The other region on the other side of the line is going to be in the non-solution region, so every point there will not work or will not satisfy the inequality. So you're either in the solution region or you're in the non-solution region. It's one or the other. Now the boundary line, there's two scenarios. There's one where the boundary line is included in the solution set. So when it's included is when we have a non-strict inequality. So basically a greater than or equal to or less than or equal to, and for this we get a solid boundary line. Now if it's a different shape you're working with, maybe a circle or an ellipse or whatever it is, we wouldn't say solid line, we'd say solid circle or solid ellipse or solid hyperbola, so on and so forth. Then the other scenario is if you have a strict inequality. So if you have something that is strictly greater than or strictly less than, you get a dashed or broken up line to show that the boundary line is not part of the solution. So how do we get the boundary line or the boundary in general? Essentially, we look at the inequality symbol and we replace it with equals. So I would have 6x plus 2y is equal to 12. I can easily solve this guy for y and graph the resulting line. So let's subtract 6x away from each side of the equation. That'll give me 2y is equal to negative 6x plus 12. Let me divide both sides of the equation by 2. And we'll see that this will cancel with this, and I'll have y by itself. This is equal to negative 6 over 2 is negative 3, then times x, then plus 12 over 2 is 6. So this line right here is very easy to graph. It has a y-intercept of 0,6 with a slope of negative 3. So the first thing we would do is graph this line, and we would graph it as a dashed line because we have a strict inequality here, strictly greater than. And so let's go to the coordinate plane, and I've pre-drawn everything today just to make it a little bit quicker for us. But again, the y-intercept occurs at 0,6, which is right here, and the slope is negative 3. So down 3 to the right 1, down 3 to the right 1, down 3 to the right 1, so on and so forth. We graph our line. Again, this guy is dashed because it's not included in the solution. Now for the next part, you basically had two options. You could solve this guy for y, and you could shade based on the direction of the inequality symbol. Or you could use a test point. So for today, we're going to go back to this test point method. And with a test point, I can choose any point on the coordinate plane that is not on the boundary line. So if I go back down, I like to use 0, 0 because it's easy to work with. It's not on the boundary. So let's go back up. So our test point is 0, 0. So essentially, I'm going to plug in a 0 for x and a 0 for y. And what I want to know is, do I have a true statement? This would go away. This would go away. You'd have 0 is greater than 12. Is that true? No, it is not. This is false. Since 0, 0 does not work as a solution, we know it lies in the non-solution region. So you can think about this area right here that's beneath or below the line as the non-solution region. So this is the non-solution region. So everything on this side of the line does not work as a solution to the inequality. Anything on the other side of the line, or above the line, you could say, works as a solution. So I would shade everything this way. This is my solution region. And on each example here, I included a computer graph. So you can see it did it perfectly. It shaded everything above the line, and it kept the line dashed. And the reason it does that, again, is because the line is not part of the solution, but anything above the line works as a solution to the inequality, and so it's part of our solution set. All right, now let's jump in and look at our first example where we have a nonlinear inequality. So we have x squared plus y squared is less than or equal to 9. Again, the first thing I want to do is graph the boundary. So now I'm not going to have a boundary line. In this case, if I replace the inequality symbol with equals, I'm going to have a circle. So the circle is going to be the boundary. So let's do x squared plus y squared equals 9. So this is a circle that has a center at the origin and that has a radius of 3, right? The square root of 9 is 3. So the center is obviously at 0, 0, and the radius is 3. This guy right here, remember this is a non-strict inequality, so I'm going to have a solid boundary. I go to my center, and from the center I go 3 units to the right, make a point, 3 units down, make a point, 3 units to the left, make a point, 3 units up, make a point. So I have my circle. I would obviously sketch the graph around those points. And so again, it's a solid graph because it's included in the solution. Now, the next thing we want to do is use a test point. Let's use 0, 0. It's not on the circle. It's the center of the circle, but it's not on the circle. So 0, 0. Let's go back up. So if I plugged in a 0 for x and a 0 for y, what would I get? I would have 0 is less than or equal to 9, which is true, right? 0 is less than 9. So that tells me 0, 0 lies in the solution region. So the solution region here is anything inside of the circle. Remember, the circle is the boundary, so you're either on the inside of the circle or you're on the outside of the circle. In this case, since it's on the inside of the circle, I would shade everything inside of the circle. All of those points inside the circle would satisfy the inequality. Again, for a nice computer-drawn graph, you can see we have our circle. Again, it's drawn as a solid circle because the circle itself is part of the solution set. And then the shaded area is everything inside of the circle. So this is the solution region. Right? Everything inside that circle would work as a solution for the inequality. And then anything outside the circle would not work. Right? That's the non-solution region. All right, let's take a look at another one. So we have y is greater than x squared plus x minus 6. So again, if I want the boundary, what do we get? We replace this with equals. We'd have y is equal to x squared plus x minus 6. This is going to be a parabola. Now, it's been a while since we worked with parabolas. It was a few sections ago, but we should kind of remember how to graph a parabola. It's one of those things that you really don't forget. The first thing you want to do is find the vertex. And basically the formula for the vertex, in case you forgot, it occurs at the point negative b over 2a, comma, f of negative b over 2a. So what is a and what is b? Well, in case you forgot, a is going to be the coefficient right here for x squared. So this is a. And then b is going to be the coefficient for x to the first power. So that's b. So in each case, they're 1. So I'd have negative b, which is negative 1, over 2 times 1, which is 2. So basically, negative b over 2a is negative 1/2. So negative 1/2. Now, I want f of negative b over 2a. I know negative b over 2a is negative 1/2. So I want f of negative 1/2. What is that? It's basically where I just plug in a negative 1/2 for x, and I evaluate. So this would be negative 1/2 squared plus negative 1/2 minus 6. So let's see what we get with this. So negative 1/2 squared would be 1 over 4, 1/4. Then you'd have plus, or you could say minus 1/2. I want to get a common denominator going now, so let's multiply this by 2 over 2. We could say this is minus 2/4. Then lastly, we have minus 6. But again, let's get a common denominator going. We'll multiply 6 by 4 over 4, and and we'll have 24/4. So 1 minus 2 is -1, and then -1 minus 24 is -25. This is over the common denominator of 4. So let's replace this with -25/4. We can erase all this. So now generally when we graph a parabola, we want to get 3 points going. So we have our vertex. In this case, because the parabola opens up, we know the vertex is going to be the lowest point. So it would look something like this. So we want to try to find the x-intercepts. If we have those, in some cases we don't, we want to try to find the y-intercept. So let's take a look. For the y-intercept, I can just replace x with 0. What would I have? 0 squared is 0, plus 0 is 0, so you basically have 0 minus 6, which is -6. So if x is 0, y is -6, this is your y-intercept. What about the x-intercepts? So the x-intercepts. Well, in this case, you're going to have 2 of them. If I replace y with 0, and I solve the resulting equation, I get my x-intercepts. So you can factor this right side here. I'm going to kind of flip it around and say, this is x here, and I'll set it equal to 0 over here. And give me 2 integers whose sum is 1 and whose product is -6. Well, you could do +3 and -2. So if I have the quantity x plus 3 times the quantity x minus 2, and this is equal to 0, I can set each factor equal to 0. So x plus 3 equals 0. The solution to that would be x equals -3. So one x-intercept would be -3, 0. The other one, if I set x minus 2 equal to 0, the solution would be x equals 2. So the other x-intercept would be 2, 0. All right, so now that we have those, let's go to our coordinate plane. All right, so the first thing I will do is identify the vertex, which is going to be right here. Basically what it is, it's -1/2, which is about right here, comma, -25/4, which is about right here. Right, you think about 24/4 is -6, so you add another fourth to that in the negative direction, so you're going down by another fourth. So again, that's about right there. So this is about our vertex right there. Then our y-intercept occurred right here at 0, -6, and our x-intercepts occurred at 2, 0, and -3, 0. Now we graph the parabola, and again, notice that this guy is graphed as a dashed parabola. That's because our inequality is a strict inequality, right? So it's not part of the solution. Now, we want to grab a test point, something that's not on the parabola. 0, 0 is available, so let's check it. So our test point is 0, 0. So I'd plug in a 0 for each x and a 0 for y. And I would get that 0 is greater than, this is all gone, -6. 0 is greater than -6. This is true. So that tells me that 0, 0 lies in the solution region. So when we think about the two regions here, one would be inside the parabola and one would be outside the parabola. Remember, the parabola is the boundary. It's separating the solution region from the non-solution region. So everything inside the parabola would work as a solution for my inequality. And then here's a computer-generated image. Once again, you have a dashed parabola to show it's not part of the solution. And then everything inside of the parabola is shaded to indicate that this is the solution region. Right? Anything outside the parabola will be in the non-solution region. All right, so let's take a look at one more of these, and then we'll look at some systems. So we have x squared over 16 minus y squared over 9 is greater than 1. So again, the first thing we're looking for is the boundary. So if I had x squared over 16 minus y squared over 9 is equal to 1, I'd be looking at a hyperbola, again, because of the minus sign there. And then again, because this is the positive one, we know this is a horizontal hyperbola. And specifically, it's a horizontal hyperbola that is centered at the origin. So I know in this case, I won't have any y-intercepts. I'll just have x-intercepts. So to find those, it's very, very easy. We know y is 0 in each case. And the shortcut is just to take this denominator here and take the principal and the negative square root of that. Plus or minus the square root of 16 is plus or minus 4. So the x-intercepts would occur at 4, 0 and -4, 0. So now the next thing you want to do, you can either find your asymptotes and then graph it that way, or you can find the rectangle, and then from the rectangle, you can extend from the diagonals to find your asymptotes. So however you want to do it, I'm just going to do everything so you have a complete understanding. The rectangle, there's 4 endpoints, and I want you to remember how we go about getting those. So everything is looking at the denominators, right, and messing with the square roots. So it's x comma y. So I look underneath x squared, I have 16. Take the square root of that, I get 4. I look underneath y squared, I have 9. Take the square root of that, I get 3. That's my x comma y to kind of get things started. Then I do variations of that. So I'm going to do negative 4 comma 3. I'm going to do 4 comma negative 3, and then negative 4 comma negative 3. So that's my fundamental rectangle. Again, I can extend from the diagonals and get my asymptotes. If I want the equations for the asymptotes, it's y equals plus or minus. Your slope is rise over run. For the rise, take the square root of what's underneath y squared. The square root of 9 is 3. For the run, take the square root of what's underneath x squared. The square root of 16 is 4. So y equals plus or minus 3/4 x. So we have everything pre-drawn, but again, you can kind of follow along. We know that the intercepts occurred at 4 comma 0 and negative 4 comma 0. We know that the points for the fundamental rectangle were 4 comma 3, negative 4 comma 3, 4 comma negative 3, and negative 4 comma negative 3. Again, if we wanted to, we could extend the diagonals here and get our asymptotes. So those would be your 2 lines. Or you could graph it with the equations we found. Y equals plus or minus 3/4 x. Right? So if I start at the origin, if I went up 3 and to the right 4, I'd have that point. Or if I went down 3 and to the left 4, I'd have that point. So that's one line. If I start at the origin and I went up 3 and to the left 4, that'd be that point. Or down 3 and to the right 4, that'd be that point. So however you want to do it, you end up graphing the asymptotes. And so you have everything you need. Each branch of the hyperbola is going to go through the intercept, and it's going to approach the asymptote but not touch it. Now these guys, again, you see that they're dashed, and that's because we have a strict inequality. Now, 0 comma 0 is available. It's not on either branch of the hyperbola. So if I use 0 comma 0 as a test point, plug in a 0, that would be gone, this would be gone. You basically would have 0 is greater than 1, which is false. So that tells me that 0 comma 0 is in the non-solution region. So what we would shade here is everything to the right of this branch right here, and everything to the left of this branch here. That would give you the solution region for this inequality. Again, just to show you a computer-generated graph, you see this is the solution region along with this side over here. Anything outside of those areas that are shaded will not work as a solution in the inequality. All right, now let's look at a system of nonlinear inequalities. The concept here is the same. All we're doing is graphing stuff that's a little bit more tedious. So that's why it takes more time than when we work with just linear inequalities or systems of linear inequalities. So we have x squared plus y squared is less than 49. Let's start out with this one. We know that the boundary here would be a circle, and we know the boundary would be dashed because this guy is strict. So it's x squared plus y squared is equal to, square root of 49 is 7, so I might as well say this is 7 squared. So this is a circle that is centered at the origin with a radius of 7. So let's go down here. So centered at the origin, a radius of 7 means I go up 7 to make a point, to the right 7 to make a point, down 7 to make a point, to the left 7 to make a point. Again, graph my circle as a dashed circle because no point in that circle is part of the solution set. For the test point, let's choose 0 comma 0. And if I had a 0 for x and a 0 for y, I would have 0 is less than 49, which is true. So that tells me that the solution for that first inequality would be that I would shade everything inside of the circle. But I'm not done because it has to satisfy both the first inequality and the second inequality. So let's go back up. Now let's think about this second inequality here. And I'm just going to label this so I can refer to stuff. This is inequality 1, and this is inequality 2. So let's work on inequality 2 now. So this guy will be a line when we make the boundary. X plus 5y is equal to 10. And again, it's going to be dashed because we have a strict inequality. So let's solve this for y. This would be 5y is equal to, I'm going to subtract x away from each side of the equation, and then divide both sides of the equation by 5. That would give me y is equal to negative 1/5 x plus 2. So my y-intercept occurs at 0, 2, and my slope is negative 1/5. So my y-intercept, let me just erase this real quick. My y-intercept occurs at 0, 2, which is right here. My slope is negative 1/5. So down 1 to the right 5, or I can go up 1 into the left 5. So that's where that line came from. Again, it's dashed because it's not part of the solution. Now, where is our solution region for inequality number 2? Take 0, 0. You can use that as a test point. And if I plugged in a 0 for x and a 0 for y, essentially I would have 0 is greater than 10, which is false. So 0, 0 is not in the solution region, so I would want to shade everything above the line. So let's think about this. We need the overlap of the two graphs. With inequality 1, it was anything inside of the circle. With inequality 2, it's anything above the line. So essentially, the overlap of the two graphs, or the area of the coordinate plane that satisfies both, would be anything above the line that is inside of the circle. So this section right here. And just to let you see what a computer does, you can see this graph is basically perfect. You have a dashed circle, because it's not included. Also a dashed line, because it's not included. Anything above the line that's inside of the circle is in the solution region. All right, let's take a look at one more. So we have y is less than 3. We also have y is greater than or equal to x squared minus x minus 2. So let's call this inequality 1 and this inequality 2. For y is less than 3, it's a strict inequality, so the boundary line will be broken, but we're basically graphing as the boundary line y equals 3. Now let's take a look. Y equals 3 is a horizontal line, so really it's just this line here that crosses through 0, 3 on the y-axis, right? But for every x value, y is equal to 3. Now in terms of where we want to shade, y is less than 3. So any value of y that's less than 3 works. So we would be shading below the line. So anything below the line works as a solution to that first inequality. Now let's take a look at the second inequality. This guy is a non-strict inequality. So the boundary will be solid, right? And we're graphing a parabola here. You'd have y is equal to x squared minus x minus 2. This is a parabola that opens up. So we would want the vertex to start. Again, this occurs at negative b over 2a, comma, f of negative b over 2a. So again, negative b here is negative 1, and a here is 1. So the negative of negative 1 is 1. Over 2a, 2 times 1 is 2. So you'd have 1/2 for negative b over 2a. Then we want f of negative b over 2a. So we want f of 1/2. All right, let's erase all this. And I'm going to plug in a 1/2 there and also there. So f of 1/2 is equal to, you'd have 1/2 squared, which would be 1/4. Then minus 1 times 1/2 is 1/2. Let's get a common denominator. Multiply this by 2 over 2. You'd have 2/4 there. Then minus 2, I can multiply 2 by 4 over 4. That would be minus 8/4. So 1 minus 2 is negative 1. Negative 1 minus 8 is negative 9. So this would be negative 9/4. So this right here is negative 9/4. All right, so we have the vertex. What would our y-intercept be? If I plugged in a 0 for x, I would get y equals negative 2. What would our x-intercepts be? Will we have 1, 2, or 0? I'd plug in a 0 for y, so I'd have x squared minus x minus 2 equals 0. I can factor this and solve it. So we would have x here and x here. So give me two integers whose sum is -1 and whose product is -2. So you could do -2 and +1. So if I solved each one of these factors, x minus 2 equals 0 has a solution of x equals 2. So 2 comma 0 would be one x-intercept. And then x plus 1 equals 0 has a solution of x equals -1. So -1 comma 0 is another x-intercept. So let's erase this and let's graph this guy. So I'm just going to erase what we've done already. So the vertex again is at 1/2, comma -9/4. So right there. Then our x-intercepts, again, we have 2 comma 0, and then we have -1 comma 0, and our y-intercept was at 0 comma -2. All right, so we have enough to sketch the graph, which is already done for us. And again, this is a solid parabola because it's part of the solution. Now, let's think about a test point. Let's use 0 comma 0. If I plugged in a 0 for x and a 0 for y, I would have 0 is greater than or equal to -2. This is true. So that tells me that 0 comma 0 lies in the solution region. So in other words, anything inside of the parabola would work as a solution for that inequality. Now, let's think about the overlap. We know in the first inequality, it was anything below the line. So essentially, it's going to be anything inside of the parabola that's also below the line. So this section right here would be your solution region. And again, to see it with a computer, we have anything that is below the line, but also that's inside of the parabola is part of our solution set. So this would be your solution region. And then also don't forget that this part right here satisfies both of the inequalities. And so it's part of your solution region for the system as well. But just the part that is underneath that line, anything above the line no longer satisfies both. So this would be your solution region. These are points on the coordinate plane that satisfy both inequalities, and so they satisfy the system.